Somewhere inside every computer is a tiny decision. Yes or no, true or false, 1 or 0. This is a 4-bit adder, and with this, I'm going to show you how computers think. Well, to start, what is a 4-bit adder? Well, a 4-bit adder is basically just an electronic circuit that's used to add two 4-bit binary numbers. It produces a 4-bit sum and a single bit carryout, or the digit that goes in front, the highest priority digit. But how does this work in computers? Well, here's an example. Let's say you wanted to add two numbers. You start with an A and a B, where A is 10, for example, and B is 7. In classical addition, you just stack them on top, carry the numbers, and it gives you a 17. But in computers, the first thing you need to do is convert them to binary form, where A becomes 1010 and B becomes 0111. Then you stack these numbers to add 1010 plus 0111. This gives you a 4-bit sum, which is 0001 and a carry of 1. You write them in order, 1001, and this gives you 17. But what's the logic behind that? So here's how it works within the computer. You've got a full adder, first input, second input, carry in, and a carry out. Each of the full adders is one of its own circuits, but we'll come back to that later. So let's say we're adding two numbers, our A and our B again. Let's say this time A is 1101 and B is 0111, which is 13 and 7. To add that, it gives you 20. You work from right to left with binary code, least significant to most significant, and that's how you write it within the circuit. Then you use something called a truth table to add these binary digits, where 0 plus 0 is always equal to 0. 1 plus 0 is 1. 0 plus 1 is the same, 1. And 1 plus 1 is equal to 1, 0. 1 plus 1 plus 1 is equal to 1, 1. Here, the carry out would be the second digit, and the carry in will be the first digit of the last number. The first one is always 0 because there's no other operation to carry it in from. So from there, we do the simple addition based on the truth table. And with that, we end up with a 0010 and a carry of 1. Now you write that with the carry out of 0 being the rightmost digit, and you get 10100. But how does this translate from binary to decimal? Well, 10100. You can read binary form as powers of the number 2, where the rightmost digit is 2 to the 0, then 2 to the 1, 2 to the 2, 2 to the 3, and then 2 to the 4, and so on and so forth. Or in other words, 1, 2, 4, 8, and 16, then so on. So in this number, we've got 16 plus 4, which gives you 20, and we had 13 plus 7, which gave us 20, meaning our addition was right. Now, let's see how that works as a circuit. So the first thing we're going to notice is we have the same two inputs, A and B, for the two numbers that we use. This A and this B will be the rightmost digits of both of them, the A0 and the B0. Then we start with the XOR gate, an exclusive OR gate. That connects to another XOR gate, or XOR gate, but the second input from that one comes from another AND gate that we connect at the bottom. The second input from that AND gate comes directly from the first XOR gate, and the output from the second XOR gate becomes the first output. We use another AND gate connected directly to the input A and B, and then use the two outputs from those AND gates and put them through an OR gate to get the carry out, which goes directly to the next circuit. The carry in for this circuit, because it's the first one, is always 0, so we just connect it to the negative terminal. The carry out becomes the carry in of the next circuit. Now, with all that being said, this is what a 4-bit adder looks like when I built it. Now, to build this circuit, I used a bunch of parts. 2 XOR gates, 2 AND gates, a single OR gate, an unholy amount of jumper wires, and I was going to use dip switches, but then that added the aspect of a float input. So I used 5 LEDs and 5 resistors instead. Here's what it looks like when the circuit is on, but all of the inputs are 0, as you can see, because all of them are connected to the negative terminals instead of the positive terminals, where negative is 0 and positive is 1. This is what happens when we make all the inputs 1. All the LEDs light up except for the one for sum 0. What did I learn from this project? I learned how to read schematic drawings, how to draw them myself, understand the logic, read truth tables, apply truth tables, so much more. And at the end of all this, I have a calculator that adds to 16. So, what's next? With this, I'm looking to use these learnings like reading schematic drawings, using breadboards, understanding where ICs go, and building an 8-bit CPU. That video is going to be a lot longer, and I hope I can show you guys how I built it, how I wired it, the entire journey, and all the struggles. If you're looking to do a project like this, you should check out my article where I detail exactly how to do it, exactly what parts I used, and the step-by-step instructions. As always, thank you so much for watching, and stay sharp.